Another widely used block transform is discrete cosine transform. When you look in literature, you will find many different definitions of the DCT type 4, but this is the one we're going to use for this lecture. And you can see also in lesson number 2, we talk about the DCT. So the DCT type 4 that we are going to use has this equation here. We notice we have this squared root of 2 divided by capital N. We have this 0.5 here, this 0.5 here, and this analysis go from k going from 0 to n minus 1, and we have the sum from n going to 0 to n minus 1. So the characteristic here is the shift of 0.5 in the subband index k and at the time index n. So we have the 0.5 shift for subband index and for the time index. If we compare it to the DCT type 2, we see that the DCT type 2 is defined by this equation here. We only notice the difference is the ck here, this coefficient, where the c of 0 is the square root of 0.5 and the ck is equal to 1 for k greater than 0, for k going from 0 to n minus 1. So observe that the only difference is that the DCT4 also has a shift of 0.5 for the frequency index k. The DCT2 is mostly used for images and video coding, whereas the DCT4 is mostly used for audio signals. So using the definition of the DCT4, we can now construct the transform matrix and extract the equivalent impulse responses. So the analysis transform matrix becomes this here. And the impulse response of the equivalent analysis filters, they are the time reversed columns. So this is the impulse response of the equivalent analysis filters. So in this way, we get capital N impulse responses. So the synthesis impulse responses are simply the rows of this transform matrix, which in this case is identical to the columns. So we have here the synthesis impulse response. So here we have our transform matrix, and then we get the impulse response of the analysis filters as the time reversed columns of this matrix, and the synthesis impulse response are the rows of this transform matrix, and in this case is identical to the columns. So we see that they are simply the time reversed analysis filter. Because here we don't have time reversal. Here we have perfect reconstruction filter banks with critical sampling, both desirable properties for coding. But our equivalent filters, they are restricted to a length of capital N. This leads to filters which do not really have good frequency responses. We can get wide transition bands for our bandpass filters relative to the width of the passband and not enough stop band attenuation. So in Python, we can get the transform matrix for the DCT using this here. So here we're starting with empty zeros, 4 by 4 matrix, n is equal to 4. Then we will iterate through n and k, and we will set these values here. And then we have our transform matrix for the DCT4. And now we can plot the frequency response of the analysis filter, for instance for subband k equals to 0. So now I'm importing SciPy signal and I'm importing matplotlib pyplot. So we will plot the SciPy signal. Once again, we use fracz to get the frequency response. It's done here. This time we're using subband k equals to 0. And then we plot here and we see the magnitude response for the DCT4 subband k equals to 0. Here we have our normalized frequency going from 0 to pi, and here we have our magnitude in dB. So observe the low stop band attenuation of less than 20 dB. A solution is to allow filters with longer impulse response, longer than the block size n. This would lead to non-square transform matrices. but non-square transform matrices are not invertible in general. We can only obtain a pseudo-inverse. Hence, we would lose perfect reconstruction, which is a problem. Alternatively, we could have overlapping blocks, which could provide perfect reconstruction, but then we would lose critical sampling. Again, a problem for coding applications. Our goal is to obtain longer filters, have the same block length for critical sampling, and perfect reconstruction. This means the transform matrix approach, or views, comes to its limits. We need new tools. This leads us to the polyphase representation, which can be seen as an extension of the transform matrix approach or as a mixture between the transform view and the filter bank view.